So our application is are superconducting magnets for future accelerator colliding accelerators. So I'm going to show what is the mission of our research in this sense, the basic concepts on superconducting magnets and how this determines some specific requirements on what we have to achieve in the superconductors on our end. Then, of course, when you have to achieve some specific requirements on a material, you need to have a lab to characterize those properties. I'm going to show a little bit our capabilities. Then I'm going to just give one example of what we did specifically to this niobium-13, superconducting niobium-13 material, but we have worked with a lot of, this is a low temperature superconductor, but we've also worked with high temperature superconductors. But within 20 minutes, I'm going to show one example, and then I'm going to show how from this research one can sometimes find products, I call them here side products that benefit other areas and conclusions. So the lab that I started establishing more than 20 years ago is called the Superconducting R&D Lab at Fermilab, and it started really very small, but because its mission has always been that of understanding and improving both the scientific and engineering aspects of the superconducting strands, wires, and cables, because superconducting magnets are made of cables which put together dozens of wires to limit the inductance of the magnet itself. And recently we have achieved a world record field of 14.5 Tesla in an accelerator dipole. We achieved that in 2020, last year. And we work in the framework of high energy physics. So as I mentioned, this is why our application are future colliders. So this is an example of our milestones, what we achieved in these last 25 years. So maybe the most important thing that we did on the material side was to advance and help industry to develop the appropriate wire to make these magnets work. And I will show you why they didn't work and why now they work. But we also worked with Japanese colleague on niobium aluminum, because in the US they had abandoned this material, but the Japanese are still working on it, and we made it, we established for the first time the use of this conductor in magnets, because we were able to put copper as a stabilizer around it, and nobody was able to put copper on the precursor, on the superconducting precursor. And then we developed also this Repco solenoid, and we produced 21.5 Tesla, which is not the record field in the world, but it was a record field in our lab. And our lab has also served as the perfect environment to grow graduate students in applied superconductivity. So the superconducting magnets follow the basic Biot-Savart rule. So their field is determined by the current and the geometry that the magnet has. So the simplest form is the solenoid, where the field is axial, is parallel to the solenoid axis. Then you have the toroid, the axial toroid, that is used in plasma confinement, for instance, or in fusion reactors. And then you have our type of field, which is called the transverse dipole. So practically you have like these two shells where the current goes inside the screen and come out on the other side, and it creates a vertical field. And of course they come with a lot of multipoles, but what you want to have is the purest dipole. So this is just to give you the context, the word context of where we are at with the values of magnetic field for accelerator magnets. So you can see it's a very slow progress, very slow progress. So here in this plot, I'm showing the field, the Bohr field, the field that the particles in the accelerator see through these magnets as a function of time. The superfluid helium are the open dots, sorry, and the blue and green are both at 4.5 Kelvin. You can see the green line represents Fermilab. So we had a very slow start, you can see here. Then we achieved, then we found out what was wrong, both in the superconductor and in the magnet technology, which is very complex. And we were able to achieve world record, whereas our counterpart, Berkeley, Lawrence Berkeley National Lab, they started, much faster. At this point, I would say nearly 30 years ago, they started very well, and then they achieved a plateau. So this is to give you an idea of how progress can evolve in different groups. So this is an example of the complex system that are these magnets. Here you can see the two shells that I showed before in a schematic. So the current goes in on this side along the magnets and comes out on this side, and you get your dipole, vertical dipole that bend the particles in the accelerator. And the superconducting coils are these copper-colored shells. But then you can see that these magnets are very complex, because they produce huge Lorentz forces due to the large currents and large fields. And so you need a very, very strong mechanical structure around. Plus, all of these operate at, helium temperature, so you have a lot of differential thermal contraction loads, and it's very complex. Anyway, this is just to give you an idea. These are the magnets that correspond to this magnetic field, if you are interested, both from Berkeley, CERN, and Fermilab. And this is our record magnet, world record field magnet here. And here I'm expanding a quarter of the superconductor, of the superconducting coils. You can see it has 4 layers, and each of these little segments is a Rutherford cable that I'm going to show you later. So see, each of these little segments is this Rutherford, so-called Rutherford cable. It's made of 2 rows of superconducting composite wires. And the superconducting wire is this one, and it has a copper matrix in which these superconducting elements, niobium tin, are embedded. So practically, these little circles here are the tin pools. These are tin rods, and they are surrounded by dozens of very small niobium filaments. And when you receive the wire, it is not superconducting, it is a composite. But then you fabricate your Rutherford cable, this one, and of course you impress huge strains, and you go into plastic mode on the material. And this is the cable from top with its insulation, and the insulation is a ceramic, it's glass, so we use ceramic a lot. And then you have to heat treat this cable. First you wind your coil, and then you heat treat the whole coil, and that's where the diffusion of the tin occurs. So the tin diffuses into the niobium filaments and form the stoichiometric compound niobium-3 tin. So it's a very complex system. From the wire, composite wire, niobium tin composite, to cable fabrication that puts it in plastic strain. Then you insulate the cable, then you wind the magnet, then you heat treat the magnet, and during heat treatment you have this niobium tin diffusion to form the superconductor, and then the material that you form is brittle. It's absolutely brittle and strain sensitive, so if you touch it, it loses in its current capabilities because strain affects current capabilities. So this is the context in which we are working, and there are a lot of other factors that are important. Like if you want to use the magnet in an accelerator, you have to, the performance has to exceed, the nominal performance in the machine, because you want to have some margin during operation. Then I mentioned the mechanical forces, the support structure, and now actually this is our bottleneck, because the materials, stainless steel, Inconel, and the conductor itself especially, cannot take more than some megapascal of pressure, and after that, the yield stress, we are going very much beyond the yield stress of, the superconductor and the structure material. So that's where we are. The bottleneck now is not in the current capabilities, but in the mechanical features of these materials. And then I mentioned field quality and magnetic stability, which are important to show you how we improve this wire. So the magnet designer, they come to you and they say, okay, we need this feature. So for instance, they need, of course, you know, the best current capabilities. So this is the critical current density of your superconductor. And we express typically at helium temperature and 12 Tesla because we are shooting at fields, at very high fields in ampere per millimeter square. So we are now on the level of 3000 ampere per millimeter square at this temperature and field. And then you see the so-called effective filament size, which actually is pretty much the size of the sub-elements of the niobium tin little elements that I showed before. And they need to be limited in size. Why? So, first of all, the critical current density determines the performance of the magnet. And how do they determine what they need? So, based on the design, there is a load line. So here you see how much current in the vertical axis you need to throw into your magnet for the magnet to produce some given field. So for instance, if they want to achieve at 4.5 Kelvin, they want to achieve, let's say, 16 Tesla, they need a superconductor whose critical surface, these are the critical surface of the superconductor of the niobium 3 tin at 4.5 and 1.9 Kelvin. So the point of intersection between your load line and the critical surface of your superconductor determines, in principle, the potential performance of your magnet. So here you can see we are in the region above 15 Tesla. However, then when they design the magnet, there are three fundamental stages of design. The room temperature stage, when, you know, the magnet, you have assembled your magnet, you have pre-compressed it in its mechanical structure, and it sees, you know, a certain distribution of strain, which I'm showing here. Then you cool it down at 4 Kelvin, and the differential thermal contractions come into effect, and it completely changes the stress distribution in the coils. And then when you throw the current in there, you throw your, you know, 15,000 amps or whatever it is, again it changes completely the stress distribution in this third stage because of the Lorentz forces. So it's very complex. Anyway, they come to you with a given minimum amount of critical current density that the superconductor has to provide. And then another very important feature of magnets is that the superconductor is magnetizes and the opposite way that iron does. It's a diamagnetic material. So you can see that when you put it in a magnetic field, it has its own magnetization curve, you know, and this is due to the fact that when you put a superconductor, each one of these superconducting sub-elements magnetizes, and it generates these two opposite currents in the filaments that go along and come back, and this is why we have the magnetization curve. And as you can imagine, this creates a lot of trouble both on the field quality, magnetic field quality in the magnets, but also, and that's what we found out, it creates magnetic instability, which I'm going to show you later. So this is my superconducting lab, which actually is not mine anymore. Now it's under somebody else's administration, but this is, you know, the one that I founded, and it's still there and useful for a lot now of different programs, not just for us. So we have these 4 magnetic cryostats. 3 of them have very high field solenoids where we do our experiments in magnetic field. Most of these cryostats are equipped with an anti-cryostat where you can change your temperature by pumping in it, you can go down to 1.4 Kelvin. These are not equipped to go to the lowest possible temperature, so 1.4 is very good for us. And then you can also go up to 100 Kelvin in this anti-cryostat. That's where we do our temperature variable experiments. These are the ovens where we do our retreatments of low temperature superconductors in inert argon atmosphere or in oxygen atmosphere. This is visco conductor, for instance, high temperature superconductor visco 2212. You need to heat treat it to form the superconductor in oxygen, and sometimes even under very high pressure. So anyway, and this is the rest of the lab. Here are all the setup, a lot of the setups that we designed. So just to give you an idea, the first setups that we designed were probes to measure the critical current. So we started using the ether barrel, which had been developed within the fusion community. So I started with that one because it was already developed. And here the current flows through the sample just through pressure contact with indium. But this limits the amount of current. So the more industry was making progress on these materials and the better they became in current, we had to change copper to copper contact to transfer the current. We developed too much resistance, so we had to go into the soldered contact. And these are long and thin because you have to plug them into this cryostat within the bore of this test solenoid at the bottom. Then we designed this very simple balance coil magnetometer to measure hysteretic curves of these materials. This is a very cheap probe made of G10, but you can also buy much more expensive vibrating systems for this. But we had limited resources, so we tried to do our best. This is a device that we designed a long time ago to measure the effect of transverse load on the Rutherford cable itself. So we apply a pressure with an hydraulic cylinder, and then we measure the critical current performance on a single wire, so we didn't need to use huge power supplies. Because another thing is that in these small labs, you know, you can only go to a couple of, on the 1000 ampere level in your power supplies, because as soon as you go to cable current power supplies like 20,000 amps, 30,000 amps, you need whole rooms to house those power supplies. They're very large. So what we did was to use the concept of the superconducting transformer here. So you can look at this one on the bottom left, which has a primary coil inside, which induces like close to 30 kiloamps on your secondary. So that's how we resorted testing our niobium-13 cables, which goes very easily to this level of currents by just powering with a few hundred amps a superconducting niobium titanium primary. So this is all the work that was done in our lab. At some point we needed to test the shielding capabilities of magnesium diboride tubes. So we designed a very simple probe to house hole probes to measure the fields inside and outside these tubes. This is the Turk head with which we make our Rutherford type cables. So this is these are massive bulk machines, but this is actually very compact. It's one of the most compact machines in the world, so we can use it for R&D. This is a Walter spring device that we designed to measure the strain sensitivity, the axial strain sensitivity on wires, as I mentioned, on niobium-13 and niobium aluminum wire. So just to give you an idea, this is the cabling machine. These are the mandrels around which that are inserted, held into this Turk head from this side, and where the wires wound around, and then out of this Turk head you have your Rutherford cable completely formed and flat. So anyway, this is just to give you an idea. This is a list of equipment. So anyway, based on the field that we wanted to achieve of 15-16 Tesla, and based on the properties of both low temperature and high temperature superconductors, of course, the best candidate was this niobium-13, which is why we did all this work with this niobium-13. So then another problem that you have when you study these materials is like, you cannot just look at the round materials. Like in the US academia, they do a lot of studies on the microstructure of the round wire, after retreatment. But we have to go beyond that, because we have to put this wire, as you saw, in this Rutherford cable, and this generates very, very huge strains and deformation of the whole structure. And of course, it affects the microstructure. So among the studies that we had to do was to check what happened on wires when extracted from the Rutherford cables and before being heat treated. So we still were dealing with a composite, but with a composite under plastic strain. So this is a complex system. And of course, we did finite element modeling to try and simulate the deformations and the behavior of this composite that was not superconducting yet. So these are examples, okay? So let's check how much the subelement deforms in these wires. So, you can come up with, a definition of deformation. This was the definition that we used, but it's not written in any textbook. You can choose your own criteria. So this was a definition of subelement deformation. And for instance, the fraction of filament that had such dimension here on the x-axis, there is the dimension of the filaments. And you can see, for instance, the round wire has its own filament distribution. So nominally, let's say the filaments have to be 50 micron in diameter, but of course you are going to find a distribution of their sizes because they come out of extrusion and drawing, and of course you have a distribution. But when you look at the extracted wires, as you can see, the average size of the filament goes to the right, it increases, it flattens, it deforms, and the standard deviation, of course, expands, increases. So this is an example. Or we came up with a definition of deformation of the wire itself in the cable, not of the single little filament in the wire, but of the wire itself. And of course, this is the Rutherford cable. On the x-axis, you can see the strand location according to this legend. And of course, you can see the largest deformation of the strands at the two edges of the cable, as expected. And also, the deformation, the average deformation of the wire itself increases with how much you compact the cable. So you have a lot of parameters in this business. And I'm not even talking of the magnet here, just I'm at the cable stage now, at the Rutherford cable stage. So for instance, what happened is that when looking at the optical images and SEM images and microstructure, but this, I think this was done just with an optical microscope. Here you can see the thin niobium element that I showed before in this restacked rod process, niobium-13 wire that we ended up using. You can see how they deform in the cable, and you can see how they merge. So for instance, when we measured the magnetization of this wire, we found magnetization curves with an amplitude that was much larger than in the round wire, because the magnitude of the magnetization behavior in these materials depend on the size of this filament. So once that they start merging together, you produce a much larger magnetization. And this is why our magnets didn't work, because the magnetization was way beyond the value that would make them work at the low field. It's called low field magnetic instabilities. When you have your superconducting filaments that are too large, your magnets are magnetically unstable. And this was found out decades ago in the niobium titanium magnets, which are now used all over. I mean, any accelerator now in high energy physics is made of the prior superconductor, which is niobium titanium. And this conductor, niobium-13, as I showed you, has a much larger, much higher critical field, and that's why it's now used for high field magnets. But it didn't work because of these magnetic instabilities due to this problem. Here I'm just showing a powdering tube type of niobium-13. There are several types, but this one couldn't be used because it just broke under cabling. So you see, there were a number of different types of niobium-13 conductors, so you have to decide which one works in your cable. The powdering tube didn't work, so we went with the restack rod process. However, we had to fix this problem. So this is what I just said before. In these cables here, the the deformation and the phenomena that happens are of this kind in this specific material. So what we did was we worked with industry and specifically with Oxford Superconducting Technology, which now is Bruker, and we asked them, because on one hand we wanted to improve our field quality, and you improve your field quality by reducing the size of your subelements, of your superconducting elements. So you want to go with increasing your subelement numbers. You want to have more of these filaments in the same 1 millimeter size wires, say, to improve your field quality, because as I said, the magnetization curve depends on that size, therefore your field quality. But to reduce subelements, we found out through some studies from experiments that I'm not showing here, that it would help if the subelements, if the superconducting elements were spaced. Because actually, you know, this merging happens not as much during the heat treatment itself, when everything diffuses, but, you know, contrary to intuition, for me at least, I thought it would happen, you know, in the heat treatment stage where you have thin diffusion and everything may get glued together. But actually we found out it happened during the plastic deformation in cable fabrication. So we asked industry to separate the subelements, and if you can believe it, once that they were separated, even when subject to such high plastic strain, they would not merge as much. And that's how we solved the big problem of the magnetic instabilities at low fields in this magnet, and how we were able to produce this, the first 11 Tesla stable magnet, 11 Tesla dipole. You can see they're very, very long, and they're put along these accelerators. And this is a short model. We typically do research on 1 meter model, but in machines, they're like 10, 20 meter long. So this is how we solved the problem, and it took us a few years. So anyway, this was achieved, I believe, in between 2012 and 2014, we achieved this. So now I'm going to show you a side product of this work. So for instance, while working with graduate students, etc., I wanted to verify a theoretical phenomenological model on flux spinning in A15 superconductors. So in these granular superconductors like niobium-13 and niobium aluminum. So a long time ago, with a theorist, we made a model that tried to explain the physics of flux spinning. So I wanted to check this model experimentally, and just for the purpose of checking the model, I'm like, I'm going to use ribbons. I'm going to use, you know, thin films to systematically check the effect of this or this other property on the model. And this is how we came up. In order to produce niobium-13 films, we tried all sorts of methods, you know, from sputtering to atom deposition, etc. And finally, we found out that simple electrochemical deposition works very well. So in collaboration with the Politecnico of Milano, we were able to develop a recipe. And so you can see we took a niobium substrate and did electrochemical deposition of a copper layer, a tin layer, and a copper layer, because to diffuse the tin in the niobium, if you have a three-element system, adding the copper, you can obtain the diffusion at much lower temperature than if you had a binary system. That's why we put the copper in there. Anyway, so we were able to produce this niobium-13 layer here. And so this opens the way to a lot of other applications. For instance, superconducting magnetic shielding, or superconducting radio frequency cavities. Now all the rage is on, you know, coating niobium cavities with niobium-13, and they do it through vapor tin diffusion in large ovens, but it's not very well controlled. So they put the cavity in there with a lot of tin sources, these big shell cavities, and the tin diffuses in the niobium. But of course, you know, you can imagine that with electrochemical deposition, we would have a much better control. Unfortunately, this research was not funded so much in the US. So finally, it was picked up by the Japanese. So the Japanese, with whom we were collaborating within a US-Japan collaboration within high energy physics, they came to Fermilab. They learned the know-how and the recipe, and they transferred it to industry. So now we have Japanese industry trying to make this a 3D process in order to apply it, for instance, on superconducting radio frequency cavities, also for accelerators. So these are, you know, diagnostic tests that were done on these films by Politecnico of Milano. So like glow discharge optical emission, X-ray diffraction, and this showed the presence of niobium-13 after retreatment on these films. And here I'm showing our tests at Fermilab of the critical temperature that is measured by measuring the resistance of the film as a function of temperature. And when you see the transition from zero resistance to a finite resistance, you have your transition to superconductivity, and you can define your critical temperature. And here I was even measuring the transport current in these films. Anyway, this was just to give you an idea of side products that were obtained through the research on niobium-13. So in conclusions, the work on optimization of these niobium-13 wires for our very high field accelerator magnets for high energy physics actually continues in collaboration with industry and university. It's very much a global research. This is Japan is involved, Europe, CERN are involved, and of course the US are involved, because we still want to improve JC, the critical current density in these materials, and now the research going on through artificial pinning centers that looks very promising and has already shown that it works on very short samples. So now we have to scale up to longer wires. And also we need to improve the heat capacity, the specific heat of these conductors, superconductors, because this would very much improve their stability under temperature fluctuations in these magnets. So what did we achieve with this improved conductor, this improved wire that allowed for stability, magnetic stability in magnets? Well, not only we were finally able to push the field to a world record of 14.5 Tesla for accelerator dipoles, but this wire is now also presently used in the framework of basic energy sciences at the Argonne National Lab. We have already fabricated samples of planar undulator magnets made of niobium-13. So these magnets, there had been several attempts in the past decades to make them out of niobium-13 to increase the field of this undulator, which could push the capabilities of light sources to diagnostic materials to, you know, it would expand tremendously the capabilities of light sources if they could push the field of the magnets producing the photons. So practically, this was done now at Argonne. So this is an example of how energy physics know-how can help other areas of physics, at least here in the US, but in this application fields, you know, you have all these complexities, and a lot of work has been going on. Thank you.